Okay, so we're going to continue talking about the environment here, and we've got a few more objectives, but there's not too many more slides. Now, the first thing that we're going to talk about is something called a psychrometric chart. Okay, there is a lot going on in this chart, and we will likely have you use one of these in class just to help you better understand what's going on. But basically, if you look at this, we've got 4 different variables here. So we've got water vapor pressure, what we call wet bulb temperature, humidity, and then we've got dry bulb temperature. Okay, and so let's go through this here. And so just so you're clear, so we've got so purple goes with the purple, blue goes with the blue, red goes with the red, green goes with the green. Okay, so there are 4 different lines on here. Now I want you to look at this, and let's just take a couple of these variables at a time. So based on the temperature, so I just want you to focus on dry bulb temperature and water vapor pressure. Okay, and so water vapor pressure is essentially on the y-axis. Dry bulb temperature is on what we would consider a normal x-axis. So what's the relationship between dry bulb temperature and water vapor pressure? And if you look, the hotter it is, the higher, the greater the value can be of the vapor pressure. Okay, this is why summers in Indiana suck. Okay, so I've struggled since I've been here. I've experienced 5 summers here. I lived in the Caribbean for 2 years, so I experienced 2 summers there. I've never gotten used to the humidity. I don't like it. It's always nice to go back home to see my parents where it is dry, and sometimes too dry, but that's another story. I can deal with that a lot easier. Okay, when it is hot, hot air can hold on to more water than cold air. Okay, and so let's just say 30 degrees here. Okay, so 30 degrees is right here, all right, on this line, and that can hold about 32 millimeters of mercury, okay, of water. That's, okay, so just remember that. So at 30, we can hold 32. Well, right now today, it is about 50 degrees outside, and so we're going to go right here. Okay, so we've cooled off, so 30 degrees, just so everybody's kind of on the same page, this is about 86 Fahrenheit. Okay, and 10 degrees is 50 degrees Fahrenheit. Okay, at 50 degrees, water vapor pressure is about 9 maximum. That's the most that it can hold. So we drop by 30 degrees, which is a fair amount. Like, don't get me wrong. Excuse me. The air is only able to hold about 2/3 of the water. Okay, you can't, when it's cold, when it's 50 degrees outside, the environment, the atmosphere can only hold 9 millimeters of mercury of water. It's just, that's it. If there's more water available, this is where you get dew and condensation. That's just like, hey, I can't hold any more water as a gas in the environment. Okay, and so this is where it gets hot and sticky and that sort of thing. And so you notice we've got these curved lines, these purple lines. Okay, this is relative humidity. This is what they tell you on the news. Hey, humidity today was 75% or whatever. Okay, if humidity is 100%, that means that for a given temperature, the atmosphere is holding on to as much water as it possibly can. Whereas when I go to Phoenix or when I go to Utah, it might only be at 10%. And so at 10%, and we don't have the line that goes out that way, but we can have really low humidity in Utah, so it can be 86 degrees with 10% humidity. Well, the maximum it can hold is 32. That means that it's only at 3, okay? And so that's what we mean by humidity and things like that. And so we're going to talk about this more in class, and we're going to learn how to use this chart. So don't be overwhelmed here. We're going to go through it. Now, we're going to kind of shift gears a little bit into altitude. So we first need to know that pressure is just force per some area, okay? And so we care about atmospheric pressure or barometric pressure. They're the same thing. We measure it in millimeters of mercury, okay? Generally speaking, at sea level, which we're very close to, it's about 760 millimeters of mercury, but it changes, okay? You can have days that have high pressure, days that have low pressure. Now, they're not huge swings. It's not like we're going to go from 760 to 500, okay? But, 10, 20 millimeters of mercury, that's probably kind of what you'll see. And so it depends on, kind of the storms that are going on, the air masses, where you're at in in terms of latitude, and with elevation. As you go up in elevation, pressure goes down. Okay. All right. And so, like I just said, as you go up in altitude, pressure goes down. Okay. It's like a water bottle. Higher pressure at the bottom of a water bottle than at the top because you got everything weighing down on you at the bottom. Important to know, and we've said this a few times, and we've said this in this class and other classes, that where you go, that doesn't change the composition of air. It's always about 78% nitrogen, 21% oxygen, and a bunch of other stuff. Okay, so even on top of Everest, if you're there, you're still breathing 20.93% oxygen, unless you're breathing through an oxygen tank. Okay, and so this gets us into Dalton's Law. So the pressure of oxygen in the air is equal to what we call the fraction or the percentage of oxygen that's in that mixture of gases times the barometric pressure. So normally you just take barometric pressure and multiply it by 21%. Okay, so as we go up in altitude, the pressure of each gas will decrease. So to give you an idea of how this changes, we've got barometric pressure here, and we've got altitude here. Okay. And so as we go up in altitude, notice what happens to barometric pressure. So when we're in Denver's barely considered high altitude. And so barometric pressure is still about 675. So it's dropped about 10%. Okay. If we go to Mexico City, we're getting down probably closer to 20%. If you get on top of Denali, okay, that's in Alaska, so it's 20,000 feet, barometric pressure is about cut in half, okay? And Everest isn't on here, but Everest is here. This is Everest, so we're about 6.9% oxygen, and they actually measured barometric pressure up there, and it was about 250, okay? And so it can be difficult to change the pressure where you're at. It's possible. We don't have that ability, but we can change the amount of oxygen. And so when you go into the environmental chamber and they say, hey, you're at 5,000 feet, all that's happened is instead of having 21% oxygen in there, it's 17%. And so with this, we need to understand the ideal gas law. And so this is pressure times volume equals the amount of gas times a constant times the temperature. Okay, and so what does this really mean? Well, as pressure goes down, then temperature is going to go down, assuming that none of these other variables change, and then the reverse is true. Okay, so as pressure goes up, so does temperature. All right, but as temperature goes down, we lead to an increase in density. And if pressure goes up, then we have a decrease in density. All right, again, this is if nothing else changes. All right, so kind of take what we just saw there and talk about, well, how does that affect temperature? Okay, as a kid, when I grew up, I always was surprised that the mountains were cooler because I would be closer to the sun, right? I'm a couple miles closer to the sun. Okay, when you start to think about it, we're 93 million miles away from the sun. If we're on top of Everest, we're 5 miles closer. So 5 out of 93 million, not a big difference, right? So what's causing the difference in temperature? Well, obviously it's not because of the distance from the sun, because if it was, then it would be hotter on top of Everest, but it has to do with pressure. Okay, remember there's an inverse relationship, or as pressure goes down, not inverse, but as pressure goes down, temperature goes down. Okay, and so if we're at sea level and it's 59 degrees Fahrenheit, okay, which is about 15 degrees Celsius, by the time we get to Everest, that same temperature, and that's not even Everest, this is like the top of the Rockies, okay, it's about 2 degrees Fahrenheit. Okay, and we can extrapolate that even further if we went out to Everest, right? So we've got a very nice linear relationship. And so lower pressure equals lower temperature. And so that's kind of our basics for the environment. So we got one more thing about heat transfer, and then that'll be the end of this first day, and then we'll dive into heat for the second day.